In this video, we'll be looking at section 7.2, which covers addition and subtraction identities. If you don't already have your formula sheet out, you will want it. We're going to start by looking at the sum and difference identities. You will find them on your formula sheet under trigonometric identities. You have your sum and difference formulas. We're going to be using these. I did change the first problem so that we had one in degrees. So do note that for this first problem, we want to find the exact value of cosine of 15 degrees. Now 15 degrees is not on my unit circle, so I don't know it off the top of my head. If I tried to find that on my calculator, first I'd have to make sure I'm in degree mode, and then I'd go, well, what's the cosine of 15 degrees? That is a decimal answer. It doesn't want a decimal answer. It wants an exact value. So we're going to have to find a way to represent this. Now, that whole idea of using the sum and difference formulas, that's going to come into play here. If I can find two angles, alpha and beta, that can either add to give me 15 degrees or subtract to give me 15 degrees, then I can use whichever corresponding formula to help me find what the cosine of 15 degrees is. So I need to see if I can find two angles, preferably on my unit circle, because I know the sine and cosine of all of those. If I can find two angles that add or subtract to give me 15 degrees, then I'll be set. Well, hey, 30 degrees and 45 degrees, those are 15 degrees apart. So I can write it as 45 degrees minus 30 degrees. So instead of thinking of this as the cosine of 15 degrees, I'm going to think of it as the cosine. That marker doesn't want to work anymore. I'm going to think of it as the cosine of 45 degrees minus 30 degrees. I have a formula for how to find the cosine of a difference of angles. That's this fourth one here. It says I'm going to take the cosine of the first angle times the cosine of the second angle. So the cosine of 45 degrees times the cosine of 30 degrees. And then the formula says after that I need to add the sine of the first angle times the sine of the second angle. So I'm going to add the sine of 45 degrees times the sine of 30 degrees. Like I said, I like these ones on the unit circle because I know all four of these values. I can just use my unit circle. So plugging in what I know about them, the cosine of 45 degrees is root 2 over 2. The cosine of 30 degrees is root 3 over 2. The sine of 45 degrees is root 2 over 2. And the sine of 30 degrees is 1/2. If I simplify the products, I'm looking at the square root of 6 over 4 plus the square root of 2 over 4. That's an okay answer, but if you want to put it together in one fraction, you can. So we're looking at the square root of 6 plus the square root of 2 all over 4. Let's try another one. We want to find the exact value of the sine of 7 pi over 12. Well, we have these sum and difference formulas, so if I can find two angles that add to give me 7 pi over 12 or subtract to give me 7 pi over 12, then I'll be able to use that sum or difference formula. I noticed that, believe it or not, we tend to be better at working in degrees than radians, because in radians there's a lot of fraction stuff going on. So what I'm going to do is I'm actually going to convert this to degrees so that we can try to think about it that way and see if we can find our angles a little bit faster. Let's see if we can remember how to convert from radians to degrees. So we're looking at 7 pi over 12. To convert to degrees, we multiply by 180 degrees over pi. So let's see what that's equal to. I have 7 pi over 12 times 180 over pi. That's equal to 105. And we're left with degrees. So if I can find two angles on my unit circle that either add or subtract to get me 105 degrees, then I'll be all right. 105 degrees. Well, hey, there are a lot of different ways to get here. Use whichever one comes to mind first. I see it as being 60 degrees plus 45 degrees. Since the original problem was in radians, I'm going to use my radian angles. So I'm looking for the sine of, I said I was going to use 60 degrees plus 45 degrees. So in radians, that'll be pi over 3 plus pi over 4. You can check that this works out. The whole pi over 3 plus pi over 4 equals 7 pi over 12. Because if you get a common denominator of 12 here, you're looking at 4 pi over 12 plus 3 pi over 12, which is 7 pi over 12. Yay, it worked. So now I'm taking the sine of the sum of two angles. That's going to be this first formula here. Sine times cosine plus cosine times sine. So that's going to give me the sine of pi over 3 times the cosine of pi over 4 plus the cosine of pi over 3 times the sine of pi over 4. The sine of pi over 3 is root 3 over 2. The cosine of pi over 4 is root 2 over 2. The cosine of pi over 3 is 1/2. And the sine of pi over 4 is root 2 over 2. Simplifying my products, I have root 6 over 4. And I'm adding 1/2 times root 2 over 2 is root 2 over 4. That's a perfectly okay answer. Or if you want to combine your fractions, we have square root of 6 plus square root of 2 all over 4. And that's what I'm looking for. It's the same answer as last time. Wow, interesting. Next up, we are trying to rewrite the sine of x minus 3 pi over 4 in terms of sine of x and cosine of x. So it looks like I have the sine of two angles that are subtracted. That's going to be my second formula here. Sine cosine minus cosine sine. So let's see what happens if I just plug everything in. So I get the sine of x times the cosine of 3 pi over 4 minus the cosine of x times the sine of 3 pi over 4. Now you may be wondering why I'm using 3 pi over 4 and not negative 3 pi over 4. Notice in the formula that it is the sine of alpha minus beta, and then we're just using beta. So whatever's being subtracted is your second angle here. That's why I'm using the positive. Well, I may not know the sine of x or the cosine of x, but 3 pi over 4 is on my unit circle. It's right here. The sine value is positive square root of 2 over 2. The cosine value is negative square root of 2 over 2. So let's plug those in. So I'm looking at the sine of x. We said that the cosine of 3 pi over 4 is negative square root of 2 over 2. We are subtracting the cosine of x. And then the sine of 3 pi over 4 was the positive square root of 2 over 2. I'm going to clean that up to make it look just a little bit nicer. I'm looking at negative square root of 2 over 2 times the sine of x minus the square root of 2 over 2 times the cosine of x. And that's what I'm looking for. This next one is going to make you probably hit your head on the table because it looks so scary and menacing, but it simplifies to something so easy you will be amazed. We want to solve for the smallest solution. We're looking at the cosine of 2x times the cosine of x plus the sine of 2x times the sine of x, and that's equal to 1. It looks super complicated, but I'm going to try to boil this down to its bare bones. I have cosine cosine plus sine sine. Let's see if I can find a formula that looks like that. We had cosine cosine plus sine sine. That looks like this last one. Cosine cosine plus sine sine. So I should be able to take the left-hand side of my equation and rewrite it in this form. All the questions we've done so far, we've taken it from the left side to the right-hand side. This time we're going to go the other way. We already have something that looks like the right-hand side. We're going to make it look like the left-hand side. So this I can rewrite as the cosine of my first angle minus my second angle. So that will be the cosine. Picked the bad marker again. This will be the cosine of 2x minus x. That whole thing on the left-hand side simplifies to that. The right-hand side still equal to 1. But hey, in here I have 2x minus x. I know what that is. That's just x. So the cosine of x is equal to 1. On the unit circle, cosine is equal to 1 at 0. So I'm just going to be looking for x equals 0. Again, that one looks super complicated, but if you use your formulas right, then it simplifies down really nicely. Now we're going to take a look at something that looks like it doesn't apply to all of this, but really it can be helpful. We're going to try to rewrite the sum of a sine and a cosine as a different version of just a sine. So to rewrite m times the sine of bx plus n times the cosine of bx as a times the sine of bx plus c, then a squared is equal to m squared plus n squared. The cosine of c is equal to m over a, and the sine of c is equal to n over a. We can use either of the last two equations to solve for possible values of c, but there's usually two possible solutions to either of these. So if we look at whether these are both positive or negative, we can figure out what quadrant c is in, and that'll help us figure out which solution we want. I will tell you, I do not have these memorized by any means, so I keep them with me when I'm trying to solve problems like this. So we're going to rewrite -3 times the sine of 5x plus 4 cosine of 5x as a single function of the form a times the sine of bx plus c. This coefficient on sine of 5x, that's what we called m before. So m is -3. The coefficient on cosine, that's what we called n. So n is going to be equal to 4. And then b is the coefficient on x. So b is 5. We're going to try to use all of these pieces of information to rewrite this in the form we're looking for. So close. First off, we know that a squared is equal to m squared plus n squared. So a squared is equal to -3 squared plus 4 squared. So that means a squared is equal to 9 plus 16. A squared is equal to 25. We are going to take the positive answer for these. So a is equal to 5. So we know that a is 5. We already knew that b was 5. So we just need to solve for c now. I'm going to use both of these equations, and you'll see why in just a second. Setting it up, the cosine of c is equal to m, which is -3, over a, which is 5. Setting up my sine equation, I get that the sine of c is equal to n, which is 4, over a, which is 5. Cosine is negative, but sine is positive. What quadrant does that happen in? Cosine is negative, sine is positive. That happens in quadrant 2. So I need my quadrant 2 answer. It doesn't matter which equation I solve, as long as I make sure my answer is in quadrant 2. So I'll solve this first one. The inverse cosine of -3/5. I'm getting c is equal to 2.2143. That is in quadrant 2 because quadrant 2 goes from pi over 2, which is 1.57, to pi, which is 3.14. It's between those two, so I know I have the right answer. Just to show I get the same thing, if I take the inverse sine of 4/5, I get 0.927295218. And you're like, that's not the same. It's not, because this is my quadrant 1 answer. I don't want my quadrant 1 answer, I want my quadrant 2 answer. For my quadrant 2 answer, I take pi minus my reference angle, which is what they just gave me. And I'm still getting that 2.214. So now that I know what c is, I can plug that in, and I'm going to get that this can be rewritten as 5 times the sine of 5x plus my c value, 2.2143. It's all fine and dandy that we can do this, but why is that important? Well, let's try to solve an equation. If we want to solve 3 sine of x plus cosine of x equals 2, and we're going to look for the first 2 positive solutions. Well, when we had 2 different trig functions before, we tried switching one to match the other one. That only worked if one was a reciprocal or if we could use the Pythagorean identity. Well, sine and cosine are not reciprocals, and I don't have any sine squareds or cosine squareds, so the Pythagorean identity is out. I'm left to using this so I can rewrite it. Let's identify each little piece. So m is the coefficient on sine, which is 3. N is the coefficient on cosine, which is 1. B is the coefficient on x, which is also 1. Now we're going to use these formulas. A squared is equal to m squared plus n squared. So a squared is equal to 3 squared plus 1 squared. A squared is equal to 9 plus 1, which means a squared is equal to 10. Square rooting, we get a is equal to the square root of 10. Now I'm going to set up my other 2 equations. We have the cosine of c is equal to m, which is 3, over a, which is the square root of 10. The sine of c is going to be equal to my n value over a, so that will be 1 over the square root of 10. you'll notice that both my sine and cosine are positive. Which quadrant has sine and cosine both positive? That's quadrant 1. So I'm looking for my quadrant 1 answer. It doesn't matter which one I use as long as I make sure my answer is in the first quadrant. So I'm going to take the inverse cosine of 3 over the square root of 10. 0.3218, that is in quadrant 1. So that's going to be my C value. I'm looking at 0.3218. So I'm going to go ahead and rewrite this in the form we want to use. So the form we want to use is A, which is the square root of 10, times the sine of B, which is 1, x, plus C, which is 0.3218. So we rewrote the left-hand side. This is equal to 2. And that's what we want to solve. This takes us back to the last unit when we were solving these things. We want to get the sine by itself so that we can get closer to that x. So I'm going to divide both sides by the square root of 10. And we get the sine of x plus 0.3218 is equal to 2 over the square root of 10. And that is when I inverse sine both sides. The inverse sine of 2 divided by the square root of 10 is equal to that fun stuff. So I get x plus 0.3218 is equal to 0.6847. Now, when you take inverse sine or inverse cosine, that is when you do two things. First, you find both angles. This is the first one my calculator gave me. That is quadrant 1. Sine is positive. Where else is sine positive? In quadrant 2. To find my quadrant 2 answer, I take pi minus my reference angle. Since I have a first quadrant angle, that is my reference angle. Pi minus my reference angle is 2.4569 if I round up. So I also have x plus 0.3218 is equal to 2.4569. So the first thing you do is find both angles. The second thing you do is add 2 pi k. But I don't want to solve for x plus 0.3218. I want to solve for x. So I'm going to subtract my 0.3218 from both sides. In this first case, I get x equals 0.6847 minus 0.3218. Gives me 0.3629 plus my 2 pi k. And in the second case, I get 2.1351 plus 2 pi k. Now it asked for the first 2 positive solutions. If I let k equal 0, I get 2 solutions. I get x is equal to 0.3629, and I get x is equal to 2.1351. If I wanted more solutions, I would plug in k equals 1. Doing that, I'd get 0.3629 plus 2 pi times k of 1, 6.64. That's bigger than this one. So that would be my next answer. Plugging in k equals 1 into this bottom case, I get 8.4183. So that would give me another solution still. But in this case, I only wanted the first 2 positive solutions, which will be these 2. We have a few more identities to look at. I'd like to show you the product to sum identities as well as the sum to product identities. These are both on your formula sheet on the right-hand side. So we're going to use these to help us. Product to sum to product. See if I can find the problems we're supposed to be working on. That one. First thing, we are looking at simplifying the sine of 9t minus the sine of 3t over the cosine of 9t plus the cosine of 3t. And I apologize, there is a typo. This numerator is supposed to be plus. Work with me. So what I'm looking at is sine plus sine. I see sine plus sine as my first sum to product formula. So I'm going to try rewriting it using the right-hand side here. Let's see if I have enough room to do all of this. Show it all. Close. There we go. So my numerator is now going to be 2 times the sine of, I need to add my two angles, so 9t plus 3t and divide it by 2. And then the cosine of, subtract the angles, 9t minus 3t over 2. My denominator is cosine plus cosine. That's this one. So plugging that in, I have 2 times the cosine of, add the angles together and divide by 2, times the cosine of, subtract the angles and divide by 2. That looks super gross, yucky, nasty. Let's see if we can simplify it. In my numerator, I have 2 times the sine of 9t plus 3t is 12t. 12t divided by 2 is 6t. Then I have the cosine of 9t minus 3t is 6t. 6t divided by 2 is 3t. In my denominator, I have 2 times the cosine of, adding them together and dividing by 2, I get 6t. Subtracting them, dividing by 2, I get 3t. So I have 2 sine of 6t cosine of 3t over 2 cosine of 6t cosine of 3t. The 2's cancel out. The cosine of 3t's cancel out. I have the sine of 6t over the cosine of 6t. Wait a minute, what's sine over cosine? That's just tangent. This is the tangent of 6t. Now we're going to write the following product as a sum. I'm looking at 12 times the sine of 7x times the cosine of 3x. Well, if we want to go from a product to a sum, I think our product to sum formulas are going to be of use here. The problem is with my product to sum formulas, they don't tell me what to do with a coefficient out front. So what I'm going to do is I'm going to leave this 12 out front and just say whatever I get for sine of 7x times cosine of 3x, and multiply it by 12. So I want to take the sine times the cosine. That's this bottom one. So I'm going to get 1/2 times the sine of, lots of parentheses here. It says to add the two together. So 7x plus 3x. Now add to that the sine of, they say to subtract them. Oh, run out of room. 7x minus 3x. Get to close that, close that, close that. All right, let's see what simplifying we can do. We have 12 times 1/2 times the sine of 10x plus the sine of 4x. So I have 12 times 1/2 times all of this. Well, 12 times 1/2, that's 6. So I have 6 times the quantity of the sine of 10x plus the sine of 4x. And if I distribute the 6 through the parentheses, I'm looking at 6 times the sine of 10x plus 6 times the sine of 4x. And that's what I'm looking for.